first thing we're going to do on this worksheet is assign stereochemistry, either R or S, to the chiral carbons of these molecules, which are being represented in Fischer projections. So first thing that I'm going to do is just highlight the chiral carbons in the molecule so that we know what we're working with. We've got 3 in this molecule. This carbon is not chiral because it only has 3 bonds, and this carbon is not chiral because it has 3 hydrogens attached to it. So when we're looking at this first carbon right here, of course, we want to follow all of the same rules that we've done before. That means that we're going to begin by prioritizing the 4 substituents that are attached to this carbon, and I just immediately noted that the hydrogen atom is going to be the low priority because it's got the smallest atomic number. For the other substituents on this carbon, we have a carbon, we have an oxygen, and we have a carbon. Oxygen is a higher atomic number and therefore higher priority, so that's going to be number 1. And then for here, we have a carbon versus a carbon, which is a tie, and that means we need to look at what is attached to those 2 carbon atoms. The carbon atom on the bottom has a hydrogen, another carbon, and an oxygen. The carbon on the top has an oxygen, and we get to count that oxygen twice because it's part of a double bond, and a hydrogen. So we have 2 oxygens and a hydrogen. And what we're doing here is comparing oxygen, oxygen, hydrogen versus hydrogen, carbon, oxygen in terms of highest atomic number. This guy up here at the top is going to win because it has 2 oxygen atoms. That's going to make this a number 2. And it's going to make this one a number 3. And if that seemed kind of overwhelming, don't worry. We're going to practice this like 100 times on this worksheet. So getting ready to assign configuration, we want to remember that the horizontal bonds in a Fischer projection are wedge bonds, which means we're looking at this molecule upside down from the appropriate perspective when we're trying to assign R and S stereochemistry. When we're trying to assign R and S stereochemistry, we want our low priority group to be on a dash bond, not on a wedge bond. That just, since it's on a wedge bond, that just means we're looking at it backwards. So this looks like 1 to 2 to 3 looks like an S, but remember we're looking at it upside down, so that means that this guy right here is an R. And like I said, if that was kind of a whirlwind, don't worry, because we're about to do it 2 more times just for this molecule alone. So moving down to the next chiral carbon in this molecule, we're just going to start the process all over again. Hydrogen is our low priority. The OH, oxygen, is going to be our high priority. We have a carbon versus a carbon. That's a tie, so we need to look at what is attached to each one of these carbon atoms. The carbon on the top has a hydrogen, a carbon, and an oxygen. The carbon on the bottom has, it's the same thing, a hydrogen, a carbon, and an oxygen. Bummer. So that means we need to move even further out in our comparison, and we're going to move out to the carbon and the carbon. We're going to compare these 2 guys. Now this carbon down here, it's kind of hard to see. That's the CH3 carbon. So we're looking at our CH3 carbon versus this guy up here, which is an oxygen that we get to count twice because of the double bond and a hydrogen. That's going to make this part a higher priority than this part. So this part down here is going to be a number 3, and this part up here is going to be a number 2. Remember that our low priority group is on the wedge. We're looking at this molecule upside down. So while it looks like 1 to 2 to 3 looks like an S, we're upside down, so it is actually also an R. And again, like, just, don't give up. This is tricky stuff. Like, stay with me. We're going to do it a 3rd time for this molecule. So now we're looking at this guy. We want to assign priority to the 4 things attached to it. Hydrogen's always going to be number 4. We have a carbon versus an oxygen versus a carbon. That oxygen is higher priority, so that's going to be our number 1. We have a carbon versus a carbon, which is a tie, so we need to look at what is attached to those carbons. Down on the bottom, we have a CH3. Up on the top, we have a hydrogen, carbon, oxygen. That is higher priority than a CH3. So this is going to be our number 2. This is going to be our number 3. Don't forget, we are looking at this molecule upside down. 1 to 2 to 3 looks like an R, but we're upside down, which means that this carbon atom is an S. We're going to keep going. We've got like a whole lot more examples to do. So here's our next one. We're going to look at the top carbon first. Assign priority to the 4 things attached to that carbon. The hydrogen is our number 4. The oxygen is our number 1. We have a carbon versus a carbon. Carbon on the top is bonded to an oxygen. That's actually a double bond to an oxygen. Double bonds we get to count twice. So that's an oxygen, oxygen, hydrogen, and this carbon down here is a hydrogen, carbon, oxygen. If you're wondering, like, how exactly do I break the tie? Because sometimes it's kind of confusing. We could say, well, we're just looking for a way that they're different. They both have an oxygen, so those are going to kind of cancel each other out. They both have a hydrogen, that's going to cancel out. So we're looking at an oxygen versus a carbon, and that's going to be, the oxygen is going to be higher priority. So that's going to be our number 2, number 3. Don't forget that we are looking at this molecule upside down with respect to the RS assignment situation. 1 to 2 to 3 looks like an R. So this guy right here is an S. And then let me erase these numbers so that we can try again for the next one down here, looking at this guy. Hydrogen is number 4. Oxygen is going to be number 1. Carbon versus a carbon. What's attached? We have an oxygen, carbon, hydrogen. And then this guy down here is a hydrogen, hydrogen, oxygen. We're trying to find a difference. So the hydrogens will cancel out, the oxygens will cancel out. We've got a carbon versus a hydrogen. Carbon is higher atomic number, higher priority. So that means that this is going to be our number 2. This is going to be our number 3. 1 to 2 to 3 looks like an S, but we are upside down. Always in Fischer projections, we're always upside down for our S assignment. We have got 5 more to practice. See, you guys are going to be so good at this by the end of this worksheet. Let's take a look at this guy right here. Let me highlight those chiral carbons. Assign prioritization. Hydrogen is number 4. Oxygen is number 1. We have a carbon versus a carbon. So we need to look at what's attached. Oxygen, oxygen, hydrogen versus oxygen, carbon, hydrogen. The difference between these two is an oxygen versus a carbon. Oxygen is higher atomic number, so it wins. This is our 2, this is our 3. 1 to 2 to 3 looks like an S, but we are upside down, so this is an R. And let's get those numbers out of the way for the next one. Chiral carbon number 2, we have a hydrogen and we have an oxygen. We have a carbon versus a carbon. On the top, that carbon is bonded to a hydrogen, it's bonded to another carbon, it's bonded to an oxygen. Down on the bottom, we're bonded to a hydrogen, a carbon, and an oxygen. That is another tie. So that means we have to look further out. So instead of comparing these carbons, we now have to compare these 2 carbons to each other. This carbon up here is an oxygen that we get to count twice because it's part of a double bond versus a bunch of hydrogens. The oxygens are going to win, so this is going to be number 2, this is going to be number 3. 1 to 2 to 3 looks like an R, but we are upside down, so it is an S. And moving on to the last chiral carbon in this molecule. We have our hydrogen, we have an OH group, we have a CH3, and then we have all the rest of the molecule. And hopefully you've seen enough of these examples that you can just say, oh, that CH3 is definitely going to lose. 1 to 2 to 3 looks like an S, but it is an R. And we have 2 more chiral carbons to go. We have our hydrogen, which is low priority. We have a chlorine, which is going to be high priority. And then we have a CH3 versus this carbon with all this good stuff on it. A CH3 is going to lose for sure. We're looking at 1 to 2 to 3. 1 to 2 to 3. What kind of stereochemistry is that? 1 to 2 to 3. It's kind of funny, but that is our S stereochemistry. A fancy S, but we're upside down, so it's an R. And then, last but not least, we have a hydrogen, we have an oxygen, we have a methyl group, and the rest of the molecule. 1 to 2 to 3 looks like an R. In the Fischer projections, we're always reversing what we assigned the stereochemistry to be, because for all of these, our hydrogens are going to be on the wedge. So now what we're going to do is draw the enantiomer of each one of these molecules. And what I'm going to do is, instead of drawing it in the space down here, I'm just going to draw it right next to it. So to make it a little bit easier to see, I'm actually going to erase all of this hard work so that I can draw an enantiomer. The enantiomers are mirror images. So when we draw the Fischer projection, I'm going to start by drawing just the horizontal bonds first. We want to draw the mirror image, and I'm assuming for these that the mirror is like right here. And like I said, I'm focusing first on the horizontal bonds. Now, when it comes to the top carbon, comes to the top and the bottom carbon, these carbons are achiral. This one is achiral because it has 3 hydrogens. This one is achiral because it has a double bond. And it doesn't make sense to draw the mirror image of an achiral carbon because it's not enantiomeric. So when you're down, like when you're drawing the CH3, some students want to continue with this process of mirror imaging, and that's perfectly fine. There's nothing wrong with doing that. But there are also a lot of textbooks or instructors or whatever, people will not mirror the achiral portion of the molecule because it's not necessary. And so if you see that portion of the molecule that's not being mirrored, don't panic. It's just because you can't have an enantiomer of something that's achiral. And so the same is true for this guy up here. A lot of students are going to want to continue the pattern of mirroring, which is perfectly fine, but you're also will see a lot of resources where that group is not mirrored, which is also perfectly fine. The only thing that has to be mirrored when you're drawing these enantiomers is the chiral carbons, which are the horizontal bonds. So we're moving on to this one right here, and we're going to be real classy chemists and not mirror the very top and the bottom because it's not necessary. And that's just kind of showing everybody that we know exactly what we're doing here. This is like a stereochemistry flex. So here's the enantiomer for this guy. All that I'm mirroring are the horizontal bonds. And then for my last one over here, mirroring this guy like that. So those are the enantiomers, the mirror images of these molecules. Now the last question is asking us to draw a diastereomer. In a diastereomer, so going back to this molecule right here, we're going to change the stereochemistry of at least one of the chiral carbons, but not all of the chiral carbons. So at least one of them has to change, and at least one of them has to stay the same. And because there is a lot of variability, so when we're being asked to draw a diastereomer, there's going to be several diastereomers that we could draw for this molecule. There isn't just one correct answer like there is with enantiomers. So for the diastereomers, I'm going to do the same thing. I'm going to draw them in these spaces up here. And what I'm actually going to do is just modify these structures a little bit so that I can draw the diastereomer. And I'm just going to be erasing the horizontal bonds because, again, when we're drawing enantiomers, when we're drawing diastereomers, the only thing that we're focusing on are the chiral carbons. The rest of the molecule does not matter. So what I'm going to do is change the stereochemistry of the top carbon for this first example, but I'm going to leave the stereochemistry alone for the other 2 carbons. So here I have drawn a diastereomer. I've changed at least one, but I haven't changed all of the chirality. So this would be one example of a diastereomer. For this one over here, I'm going to do the same thing. I'm going to change the stereochemistry of the top carbon, but I am going to leave the bottom carbon alone. There's the diastereomer for that guy. For this one, I think what I'm going to do is change the stereochemistry for the top and the bottom. So I'm going to change the stereochemistry on the top and on the bottom, but the middle one, I'm going to not change its stereochemistry. So again, the pattern here is you change one, you leave one alone, and then whatever you want to do with the rest of them, that's completely up to you. So for this last one, I'm going to change the bottom stereochemistry, and then I'm going to not change the top stereochemistry. So those are some diastereomers.